All right. Hopefully that's okay there. All right. I'll be checking back though, just in case. Hopefully making sure that the recording is working. So welcome back. I hope you all had a good break. We left off last time with talking about computation and computational models. We started out with languages and showing that languages are the same thing as problems, because you can encode any problem that you want. If it's a graph problem, you can encode it as a graph, as a binary sequence. And then you can ask whether or not an element is in the language or not in the language. And that's how languages are the same thing as problems. Then we went into different computational models. We went and we looked at finite state machines, which are very basic models. You can only read the input once. You can't go back. You have no extra memory. And you only have these finite states. But it turns out that it's still pretty powerful. You can do certain things like parity checking, whether or not something represents an even number in binary, etc. So there were some things that you could do, and you could do well in there. But it wasn't enough. What we needed to do to compute anything that we wanted that is computable was to introduce a Turing machine. And the Church-Turing thesis states that Turing machines and what we think of as algorithms are the same thing. Okay? And then we showed that even these have limits. That there are certain problems that there is no algorithm exists for them. There are certain things that are uncomputable, that are not computable. First of all, we showed that through diagonalization, showing that the number of languages is uncountable, whereas the number of machines is countable. So there are languages out there that cannot be decided by any Turing machine. Then we showed an actual concrete example called the halting problem. That given this machine and this input, we asked the question, does this machine, when simulated, when run on this input, does it halt or not? That turns out to be a problem that cannot be solved by any algorithm. Okay? So now what we're going to do is we're going to turn our attention to things that are computable. In other words, we're going to, okay, so fine, there are these things out there that are not computable at all, the halting problem and a whole bunch of other things that you can talk about. In fact, any non-trivial property about a language, it's called Rice's theorem, can be shown to be undecidable. What we're going to do is we're going to focus on the things that can be computed, the things that are decidable by a Turing machine. In other words, the things that we can actually write an algorithm for. At this point in your CS careers, you have written a lot of algorithms. And algorithms, when you've got an algorithm, you can analyze it with respect to its complexity, right? For example, order 1, right? That would be a constant time algorithm, a formula computation of some sort. Order n, give me something that's a linear time algorithm that solves a problem. Linear search, sure, there we go. Right? Order n squared. You've seen algorithms that are order n squared, for example, selection sort. Now, is selection sort the best sorting algorithm there is? Certainly not. Merge sort, quick sort, Tim sort, those are all going to, and heap sort, those are all going to be order n log n. In other words, not all algorithms are created equal, right? But all of these are polynomial. In fact, if you go for any n to the k, where k is some constant, that's going to be a polynomial time algorithm. Right? You also have exponential and super exponential, and you can just go ahead and keep piling these up and piling these up until you get larger and larger functions. It doesn't matter how slowly they run, it still decides a language, right? It's still going to be a Turing machine or an algorithm. Now, what does it mean with respect to efficiency for Turing machines? For example, what does it mean for time? Right? Usually what we're doing here is we're analyzing with respect to the number of elementary operations. That corresponds roughly to the computation time on actual hardware. So what does it mean for a Turing machine with respect to time? You remember how Turing machines work? Let me go ahead and bring up that diagram. Where is it? Here we go. Here's a Turing machine. Remember that it's got this finite state control, right? And it's reading the input, and it's possibly writing to and reading the output. So each time, each step in its computation, it's looking at the input, it's looking at the output, and then it's making a decision on where to go to next and what to do with each one of these tape heads. It could move it left, or it could move it right, it could move it left, or it could stay put. Likewise, it could move it left, it could stay put, or it could move it right on the output tape. That costs you 1 unit of time, basically. So with respect to Turing machines, time means the number of state transitions, right? In a Turing machine, time is measured by the number of transitions from one state to the next until you halt and accept or reject. What about memory? In a Turing machine, memory is ... All right, let's go back to the diagram here. So this is a generally we treat the input tape as a read only, so we're not ever going to write to it. But here's our work tape down here. This is our extra memory. This is part of the machine itself. Right? It's like when analyzing a selection sort, you don't say, oh, for I equals 0, I less than n, I plus plus I less than n. That's a comparison. Why don't we count that? Because it's necessary to the control structure of the algorithm. Likewise, this is necessary to the actual Turing machine and is not part of its memory. Instead, this is down here. So go ahead.
What are those little read things?
Is this gamma or what?
At the end of the work tape and at the end of the
These?
tape. Yeah.
Those are blanks. Those have not been written yet. You can also write a blank to it if you want to erase a memory cell, right? And you're assuming an infinite one-way tape here, so that you can use as much memory as you want, right? Just keep printing until infinity, right? That's what that means. It just hasn't been written to yet, right? So in a Turing machine, memory is the number of tape cells used in the work tape. Right? So it makes sense that we can call this, m sub n, right? We can, oops, sorry, go to the next line here. We can bound both time and memory by functions, right? T sub n and m sub n. There we go. Where T sub n will be the time that it takes to compute a Turing machine on an input of size n, right? What does it mean for size of the input then? The size of the input, n, is the ... What's the size of the input here? Hint? It's the number of... I started at 0 here. I technically should have started at 1, but whatever. It's the number of bits in the input tape. Right? So for n, is the number of bits or symbols in the input tape. So all of what I'm trying to get across to you here is that all of the analogs that you have, or all the ideas that you have of efficiency, analysis, and all those things that, the 5-step process of identifying the input size, elementary operation, et cetera, et cetera, et cetera, that all has analogs with respect to Turing machines. So it can make what you can do is you can analyze a Turing machine based on the number of transitions it takes, right? You can bound the number of transitions by some function, right? And say that T sub n is in big O of some f of n. Right, there we go. Transitions. Let me double check here. Yep, good, we're good. Okay, so you can do everything that you've done up to this point with respect to algorithm analysis with respect to Turing machines. And because we know that we can do that, what we can do is we can stay in the world of algorithms and algorithm analysis and not have to worry about those low-level details of exactly how many transitions does it make on this input, right? We can just give a rough estimate. But once you've done that, then you can go ahead and define what are called complexity classes. And the first one that we're going to be looking at is P. Right? P stands for deterministic polynomial time. Don't worry about the word deterministic yet. Polynomial time there is the operative word there, right? So P, or the complexity class P, consists of all problems such that there is a polynomial, deterministic polynomial time, or deterministic Turing machine, I should say, that runs in polynomial time with respect to any input. So pretty much everything that you've done up to this point is a problem that is in P. Almost everything. For example, sorting. Sorting is a problem that is in P. Linear search, binary search, searching is a problem that is in P. What else have you, any graph algorithm that we've looked at so far, except for Hamiltonian path, Hamiltonian cycle, shortest path, minimum spanning tree, all these problems are in P. And I want to emphasize that. P, oops, here we go, is a set of problems, i.e. a set of languages, not a set of algorithms. Right? To show that a problem is in P, you need to come up with a polynomial time algorithm that solves or decides that problem. That's all you need to do, right? So, for example, suppose I didn't know anything about the shortest path problem, right? And I don't have any algorithm at all for it yet. So I don't even know if it's in this complexity class P. But once Dijkstra comes along and shows that, yes, indeed, there is this polynomial time algorithm, even if it ran in n to the 100, that would still be a polynomial time algorithm. Then that shows that this problem itself is in this complexity class, right? The existence of the algorithm gives proof that it's in that complexity class. It's not that the algorithm is in that complexity class, because we're not talking about algorithms anymore. We're talking about problems, okay? Yeah, go ahead.
What's the difference between problems and algorithms again?
Good question. So what is the difference? Algorithms solve problems, right?
Okay.
And what is our translation here? What is an algorithm? An algorithm is a Turing machine. What is a problem? It's a language, right?
Yeah.
And what does it mean to solve? It means that there's this Turing machine that decides this language, right?
Okay.
So a machine, a Turing machine, an algorithm, those are, pseudocode. It's a Python program. It's a Java program, right? That's an algorithm. A problem is what they actually solve, right? So all of these this complexity class here is no longer not us talking about algorithms anymore. It's we're now talking about classes of problems, right? Complexity classes are classes of problems or languages, not algorithms. Right? The existence of an algorithm shows that a problem is in P or some other complexity class. There are dozens of different complexity classes. We're only going to look at 2 of them. Is in P, but if we didn't have any algorithm for a problem, we wouldn't know where it belongs or where it exists, what complexity class it is in. Right? We wouldn't know that if it's in P or not P. In fact, if we don't have an algorithm at all, we don't even know if it's decidable. The halting problem. Do I have an algorithm for the halting problem? No, we proved before the break that there's no such algorithm for it. Right? So it lies completely outside the boundaries of anything that's even decidable. Now when we consider everything that's decidable, it could have a polynomial time algorithm for it. It could have an exponential time algorithm for it. Right? Just because there's an exponential time algorithm for a particular problem doesn't mean that that problem is not in P. Right? So let me go ahead and phrase it that way. Just because we don't know poly time algorithm for a problem doesn't mean it is not in P. Right. For example, well, a typical NP complete problem, like satisfiability that we're going to look at here in a second. We don't know any polynomial time algorithm. Most people believe that there's no such polynomial time algorithm, just like it's been shown that there's no algorithm period for the halting problem. We don't know if there's a polynomial time algorithm for, say, satisfiability. Or another example, suppose, I don't know, well, one example that you're going to be working on in your 10th homework here, the longest non-contiguous palindrome problem. You can come up with a brute force algorithm to solve a problem that's exponential. That doesn't mean that it's not in P. Right? It could be that there's some other algorithm out there that is way more efficient than what you initially came up with, and that when you use that algorithm, then show that that algorithm is correct, then that takes that problem that you originally had an exponential time algorithm and it pulls it down over here into the complexity class P, showing that there is indeed a polynomial time algorithm for it. Okay. So again, what are some examples? Finding the shortest path in a graph, computing a minimum spanning tree, sorting. These are all problems in P. And to show that a problem is in P, all you need to do is come up with an algorithm for it. Right? So now let's go back to this one word that we just introduced here, determinism. Right? What is determinism? In the context of, I mean, I think that there's like a branch of philosophy called determinism and stuff like that. Don't worry, it's not the same thing. Determinism, with respect to computation, means that if you run it over and over and over again on the same input, you have the same outcome every single time, the exact same computation every time. If I run selection sort on an input array, right, it's going to end up exactly the same way as it would if I ran it once, twice, 3 times, 4 times on the same input. Okay? That's what determinism means. There's no randomness. There's no quantum entanglement like there is in quantum computing. It's all completely deterministic. That if one computation is A, B, C, D, E, then the next time you run it on the exact same input, you will have A, B, C, D, E. It will not deviate from that. Okay. On the same input, it has the same computation. So now what I'm going to do is I'm going to introduce a counterpoint to this called nondeterminism. Nondeterministic computation. Okay. So this is not randomness. Randomness. Most people, when they first see nondeterminism, they do mistake it for randomness. It is not. It is not a real computational model. If you want to have a randomized algorithm, right, and you probably have done this before where you use rand to generate, say, random inputs and for testing or whatever, right, then you can do that. That's a real computational model. You can go to random.org and you can get a bunch of random bits, right? That's real. Even quantum computing, right? People have built actual quantum computers. Whether or not it's scalable, they built small-scale quantum computers. All right, those are real models of computations, things that you can actually build. Determinism is something that you can actually build because that's what every single computer here is doing right now. Right? Nondeterminism is a theoretical model. So nondeterminism is a nondeterminism. Nondeterminism, I still don't think I got it right, is a theoretical model of computation. So how does it work? It works in two phases. So this is a simplified version of this. Of course, if you want to, you have to define non-deterministic finite state automaton. You can formally define a non-deterministic Turing machine. I'm going to keep it really high level here because this is not a course on computing. This is just an introduction to non-determinism. It works in two phases. The first phase is a guessing phase. Right? It guesses a solution to a problem, a given problem. Right? This is the non-deterministic phase. Right? There we go. And then the second phase is it's the verification of the verification phase. Right? Given the guess, it verifies if it is a valid solution or not. Right? If it is known as a certificate, right? Or witness. Right? So I'll give you a concrete example here in a moment, but it's a certificate, right? It's a certificate of authenticity. I guessed at a solution, right? And here's my guess. You verify it, and you say, oh, okay, yes, that is indeed the a solution to the problem, right? It's kind of like a lottery ticket. I'll guess the numbers that are going to come up next week, and then I take it to the lottery office and I say, please verify this. And they look at it and say, nope, those aren't the numbers that came up, right? That's not a certificate. Congratulations, those are the numbers that came up. That is a certificate witnessing the fact that you won the lottery, right? So congratulations, right? You solved the problem with that guess. There were many other guesses that you could have made that were not going to win the lottery, right? So it's this two-phase process. The first phase is the theoretical process, right? In fact, actually, the acceptance is also a theoretical model, right? So the machine, the overall machine, accepts if any possible computational branch or guess is valid. Right? So now again, this is why it's not a real computational model. Don't get hung up on this magic, because that's exactly what it is. It's magic. You cannot build an actual non-deterministic Turing machine. Right? It is a theoretical model of computation. So now to understand that theoretical model, let's go ahead and reintroduce a problem that you might be familiar with. You may not be familiar with it, I don't know. But certainly from, say, 235. Given a quantified formula like this, is it satisfiable or not? Right? So what about this one? Is this satisfiable? In other words, does there exist, so this is satisfiable if there exists an assignment to its variables x1 through xn such that it evaluates to true. Right. So you did exercises like this in 235 all the time, I assume. How did you go about solving this? Deterministically. x1, x2, x3 with a truth table. Right? So you can set them all to 0. Right? 0, 0, 0. You can set them all to 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. And what is the value on each one of these? So if I go 0, 0, 0, this entire thing is 0. And since this is an and this is an and, that kills the entire thing. Right? So this ends up being 0. It's not satisfiable yet. At least that assignment does not satisfy it. What about the next one? 0, 0, 1. So this is 0, 0, 1, or sorry, 0, 0, 1. So that makes this entire thing true. 0, 0, 1, that makes this entire thing true. 0, 0, 1. That makes this entire thing, remember, these are disjunctions, these are ors, so you only need one of them to be 1. And so what is the truth value of this one? 1. Whatever else the rest of them are. Okay? But we can already answer the question, is this satisfiable or not? Yes. Here is one truth assignment that witnesses that fact. Right? All right, let's go ahead and try a different one. You could probably tell from the file name. Is this going to be satisfiable or not?
I wasn't looking at the
So 0, 0, 0, false. So that doesn't work. 0, 0, 1, that takes care of the first one. This is true. 0 and not 0, that's going to be what? That's true. All right, so this is true, true. What about this one?
That's false.
False. So already that kills it. We don't need to look at any more. What about 0, 1, 0? Well, that takes care of this one. 0, 1. Okay, well, that kills this one, so that's also going to be false. Dot, dot, dot. I'm not going to do them all. I'll let you do that as an exercise. But all of these are going to end up being false. So is this satisfiable or not?
No.
It's not satisfiable. There is no witness to the fact that it's satisfiable. Now, for both of these, what did I have to do in the worst case scenario? I had to go through every single possible truth assignment. Given n variables, how many possible truth assignments are there going to be? There are 2 to the n, right? 2 possible assignments. So doing this brute force is going to end up being order 2 to the n, which is exponential. All right, so be it. Is there a better way? All right. What I'm going to do is I'm going to design a non-deterministic algorithm for this. So this is going to be a, oops, okay, there we go. Non-deterministic SAT. Right? So here's my input. My input will be a propositional formula on variables x1 through xn. And let me go ahead and give that a name. I'll say phi sub x. Right? That's a vector, right? X1 through xn. Right? And my output will be true if phi is satisfiable. In fact, I'm going to amend this, and my output will be to accept if phi is satisfiable, reject if not, or otherwise. Okay? So now here's my non-deterministic algorithm. Remember that a non-deterministic algorithm has 2 phases. Here's the guessing phase. Right? So get 1. Guess a truth assignment x1 through xn. In other words, if you look at, just guess one of these rows here. Guess that row, or guess that row. Okay? And then 2, verify. Right? If phi on, and I'll go ahead and give this a name, x vector, evaluates to true, then accept. Else, reject. Okay? Now, if this were a randomized algorithm, then you would see that there would only be one computational path. You randomly select one of these rows, okay? You randomly select this row, and it turns out, okay, well, that didn't work. That doesn't mean that there's not some other row that would work, right? But the thing here is that this entire algorithm will accept if at least one of its computational paths accept, okay? Here's a way of visualizing this. All right, we're going to start out here with x1. x1, you can have two choices here as your guess, 0 or 1. Right? And then you assign that value. x2, you also have two choices, 0 or 1, 0 or 1. x3, you also have two choices. And you can start to see the pattern here, right? How big is this tree going to be? Yep, 2 to the n, 2 to the n, leaves. Right? But the thing to realize here is that one particular computational path is what depth. So if we come down here and we've got this phi, this guess on phi of x vector, right? What is the depth on this thing right here? Oops. Well, yeah, if I'm doing x1, x2, x3, dot, 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 and the last one that I do down here is xn, so what's the depth here? N, right? So my guess only takes me order n time. Right? In other words, polynomial. But with the power of non-determinism. Right? Now, if I did not have this power of non-determinism, what would I have to end up doing? I'd have to go down, try this computational path. That didn't work. Back up. Go down some other computational path. That didn't work. Back up again. Go down some other. Go down, go down, go down. In other words, explore this entire tree, giving me an exponential time deterministic algorithm. The power of non-determinism here means that I can do all of them all at once, right? It's not even like parallel algorithms. Parallel algorithms, you split up the work and then run 50 different processors in parallel. That's not what this is, okay? It's just this magic thing that we accept if at least one path accepts. How do we know that at least one path accepts? We don't. That's non-determinism. That's the magic, right? We're supposing that that magic non-determinism exists. How much more power does it give us? Well, whereas before deterministic solution, brute force solution would have been order 2 to the n, exponential. Non-determinism speeds us up, order n, right? So it takes what was originally exponential, and now it takes it down to polynomial, okay? How did it do that? Who knows? It's magic. We cannot build a non-deterministic computer. We can build a randomized computer. We can build parallel computers. We can build even quantum computers. We can't build a non-deterministic computer. It is simply a mathematical model that allows us to reason about a lot of problems, including SAT. Right? Why does it allow us to reason about a lot of these problems? Maybe you remember this syntax. What is that symbol? The backwards E? Exists. Oops, n. Such that phi sub x1 on xn is 1. Let me get rid of that. Right. So you remember this from logic, right? This is, what was this again? There exists. Well, what did we just do over here? We accept if there exists at least one path that accepts. In other words, what computational power does this quantifier have, right, from logic? And this first order logic over here, that's just determinism. If I'm given this input here, of course I can go ahead and verify that value really easy deterministically, right? But non-determinism gives me the power of this quantifier. Does there exist a truth assignment such that this evaluates to true? Right? So that's why it's helpful. That's why it's nice to reason about those things. And that allows us to define another complexity class. Right? So having a non-deterministic polynomial time Turing machine or algorithm allows us to define NP. All right, so do not make the mistake that a lot of people make and think that this stands for non-polynomial. It doesn't. It stands for non-deterministic polynomial time. Right? It consists of all problems such that there is a non-deterministic algorithm that solves it in polynomial time. There we go. All right. Well, one of those things is what? SAT. Given one of these formulas, does there exist a truth assignment such that it evaluates to true? There's the algorithm for it. It runs in what time? This first phase, I'm only guessing n things, so it runs in linear time. This one, and this is non-determinism, non-deterministic. This verification phase here, I don't know, it's at most order n squared or whatever, right? I'll just give an overestimate on that. And that is deterministic. Right? If I gave you a truth assignment and said, all right, plug these values into this expression and then output whether or not that expression is true or false. You can do that pretty easy and straightforward, right? It is this phase right here that makes it non-deterministic. And so this SAT problem, satisfiability, that shows that this problem here is in NP, right? Non-deterministic polynomial time. What is the relationship between these two classes that we've just created, or that we've just defined? Right? So, comparison. Right? What is the relation between P and NP? Well, what's one very easy relation that you can come up with? Trivially, by definition, we have what? P is a subset of NP. Why? Can also be solved non-deterministically. How? By simply skipping this first phase, right? If I've got a problem and I just simply skip over this non-deterministic phase, and instead of that I go ahead and replace it with an actual solution, right? Then I've solved the problem without using non-determinism. And so that's why we say that P is a subset of NP. Remember, these are problems, right? The interpretation here is that any problem that can be solved in deterministic polynomial time can be solved in non-deterministic polytime by simply ignoring the non-deterministic phase, right? Non-deterministic phase. I'll fix that later. Right? Here's another observation. if you use an exponential amount of time, and you can always simulate a polynomial amount of nondeterminism. There we go. In other words, I can set up the following relationship. NP is going to be contained, subset equal, on this other class called EXP. There we go. What do you think EXP stands for? Exponential time, right? That you can always simulate non-determinism if you're willing to have this blow up in time. And we've seen that, right? If you are willing to traverse this entire computational tree in order n 2 to the n time, then you can, of course, check, is there at least one path that accepts, right? You can simulate this entire process with traditional old determinism as long as you're willing to invest an exponential amount of time, right? What about the other way around, though, right? The big question, in fact, the $1 million question is, let me go ahead and grab this so I don't have to write all the LaTeX again. Is it equal? That's EXP. That's exponential, right? That's what EXP stands for, right? Here's the $1 million question. Is P equal to NP? In other words, does the containment go the other way around? We know that we can simulate non-determinism with an exponential blow up in time, but in fact, is it possible to simulate non-determinism with a polynomial amount of time? In other words, can I solve this problem in particular by somehow simulating all of these possible computational paths and then accepting if at least one of them does? It doesn't seem likely, does it? I don't see how. Most people don't see how. Most people think that it's not possible. Most people believe that P is not equal to NP, right? Most think not, right? That the answer to this question is that it is not equal. Right? Most think that they're not equal. In other words, i.e., there are problems that are not solvable by any polynomial time, deterministic, polytime algorithms. And this is a very nice analog to what we were looking at before the break. Are there problems that are not even solvable by any algorithm? Yes, there are. Okay, now let's look at all problems that are solvable by some algorithm. Are there ones that are intrinsically more hard or more difficult to solve than others? Right? And that's the motivation for introducing these two classes. Right? So the question is, are there problems that are inherently more difficult than other problems? Right? In other words, so the answer to that question, to answer this question, we need, so sorting. Sorting is easy. Why? Because we have an order n log n algorithm for it, right? Satisfiability. Is satisfiability easy? In other words, could you come up with an n log n algorithm for it? Right? I don't know. Maybe you could. Nobody's proven that you can't. Nobody's proven that you can. It's a big open question, right? Until somebody comes along and says, no, there is no polynomial time algorithm for this problem, separating P and NP and showing that they're not equal to each other, then the question will remain open, right? And so that's what we mean that by relative difficulty of two different problems. That one requires more computational power, more computational time than another one, right? So to answer this question, we need a framework for comparing the relative difficulty of problems. Right? We already have a framework to compare the relative complexity of algorithms. What is that framework? Big O analysis. Order n log n is going to be quicker than order n squared. That's why merge sort is better than selection sort. It's why binary search is better than linear search. But now we're no longer talking about algorithms. Now we're talking about problems. Given this problem and given this problem, how can I say that this one is more difficult or this one is more difficult than each other? I don't even have an algorithm for them anymore, maybe. Right? Because we certainly don't know of any deterministic polynomial time algorithms for these most difficult problems, these NP-complete problems that we'll define here when we develop this framework. Okay? So we already have a framework for algorithms. What we need to do now on Wednesday is develop a framework for problems instead. And remember that they are distinctly different. Algorithms solve problems. Problems are solved by algorithms. Algorithms are Turing machines. Problems are languages. So how could I say that this one problem is more difficult than this problem, or that this one language is more difficult to decide than this language? We won't be able to make a definitive answer like that. But we will be able to make a relative statement. This problem is at least as difficult as this problem. We don't know if it's strictly more difficult. We just know that it's at least as difficult as this problem. It could be that they have the same complexity, just as it could be that they're equal. P is equal to NP. It could be that they're not equal to each other, but we can't say definitively. But we can set up a relative difficulty, with the most difficult problems being up here, the easiest problems being down here. And whether or not this entire landscape collapses and everything is equal, we don't know. All right? That's where we'll pick it up on Wednesday, though.
So the people just have to brute force